can get the display back up. Woo. By the way, do you want a chair for your foot? You're good? Okay. All right. So why, before I begin this, let me just say, I look at this as a conference. You know, you come here to learn. And so the best way to learn is do something that you don't know and present about it. So in this case, I knew something about buffer overflows on x86 because it's been around for a while. Didn't know anything about x86 64, and my ARM assembly was like this big. So it was like back in December, I was like, I want to do a presentation this year. I want to do this on buffer overflows on these three architectures. And because I have all this time management skill, I'm going to do my work and my two classes. And this is the result. So anyway, so the presentation is just like to kind of walk you through it. All the code is on my GitHub. And basically what I've done is I've set up a pen testing lab, so to speak, where you have all the files that'll start up the VMs and all the code that's going to be shown here. So we've kind of talked about a little bit of an intro, and I want to talk about a demo of a buffer overflow because, you know, some people may write them here, some people may have heard them and don't know what they are, and this is going to start at that level. I'm going to give you a little bit of background on the architecture and some techniques and tools, and then I'm going to go over the three papers for these three architectures. So, you know, what is a buffer flow? You hear about them. I think I did this slide in February, and, you know, it was like the hot topic at the time, and there you go, yeah. So here, like, it's not, I don't know if you can read that, but it's not obvious there, but that's the one we're going to look at. But here, you know, right here in the cert list, and then there's the one that was highlighted, and you find out inside, yes, indeed it is. And I'll jump in here just to kind of show you something. Oh, and the network was working, and it's not now. Okay, whatever. We won't do that. Basically, they're showing like their publish, right? Their disclosure. And you'll look inside it, and you'll see like GDB. You'll see some of the commands that we're going to be running later. So it's right into where you're trying to get. All right, so the first one I'm going to do, which came from a MOOC. I take a lot of classes in Coursera and EDX, and they had one from the University of Maryland, which was like a security class, and one of the first assignments was like Exploit 101. It was take a program that does something and make it change the program execution flow. Since it was kind of set up that way, it was not an assignment to get a shell, but it was like, hey, let's get a shell, right? So we're going to use that assignment to kind of demo, and that kind of gives you an understanding of saying, like, you know, here's a program that does this, and then we're going to exploit it and get a shell. So it kind of goes as a good intro. And it has a read buffer vulnerability rather than like a string copy. So you can pass in something that has spaces or null characters in it, and you'll see more about that later. And it also has a built-in function pointer, so it's really easy to exploit. So this is for everyone who doesn't have a clue what they are. And hopefully we can, let's not go into it. looks like that's not good. Looks like they have changed some stuff, so give me 1 second. Let's do it this way. Trying to connect. We were up here earlier and the network was working. I was using Wi-Fi earlier. It looks like Wi-Fi. So this is embarrassing. All of my demos are YouTube videos, and earlier we had a network, and I don't have my phone to tether. Try. All right, let me try this one real quick, and I'll try that real quick. IP. What's your Wi-Fi ESSID on this box? Verizon? Check button. Okay. My phone, I have tethering, and my phone's upstairs. Your screen is blank. No. This. What's your ESSID? Okay. Let me try to move this so it can't be seen. There we go. Okay. RIZ-MI. So just come over here and let's tell me if that's what that is. That's the ESSID. Yep. And then the password. Do you have a password?
Yeah, it's right there. They can hear you.
Okay.
Radio Lab.
Shorts! From
WNYC.
See?
Well, there were, like I said, it worked earlier, and that was one of the things I wanted to test, but it's not working now, and I can't even do the slides. So do you want to punt for a second and let me go get my phone, and I can just tether myself? Sorry about that. Like I said, it worked on the Hilton before we had so many people in here. But anyway, so we're going to start. So this is the first one. This is the MOOC demo, just to kind of give you a feel before we go into start looking at the code. And we'll try to make that full screen so it's readable to just the guys in the front row. All right, so this is a program. It's just showing you. It does some kind of function. You can enter some wisdom, and then you can receive wisdom. And it's using a function pointer to determine what thing to do. Then we're going to give it a malformed input. The malformed input is that selection text there, and it will then give us a shell. So that is a buffer overflow showing you how to change your input. So here is this, I'm running it with this run bin program. The echo E is to take those slash characters and convert them from printable ASCII over to actually binary, which corresponds to the machine code. The very first number, which is in plain ASCII, is where we're overflowing the index into this buffer. The next thing you see is you see zeros. You can't do zeros if it's a string copy, but with a read you can, because the zeros will null terminate the string. The A's and the B's are just spacers. So the actual code is over there starting with the XBB. And in there is a string. You see the 2F6269? That is the /bin sh. So this is the GDB file, if you're familiar with GDB. And I'm just showing where I'm going to break, where the file is. This is in the 386 directory structure of that project. So this is running on a Arch Linux i386 32-bit architecture VM. And then I'm just showing you how GDB actually runs. So that little bit of wickiness was just the video editing, cutting some frames out. And I think at this point it might be towards the end, but let's just see. Yeah, so it's like resyncing up. So here it is running in GDB to kind of give you an idea of how this works. And don't worry about if this is not real clear. This is just an intro. We're going to look at it more on the 386 code portion, and then we're going to do it again for 64 bits, and we're going to do it for ARM. So here I'm running it with that run bin, so it's running. Then I'm going to switch screens. I'm just going to Control AP and go run GDB to hit the breakpoint. There's my input that I'm passing in, and we'll kind of see how it changes in the code. So there is inside of the code, hitting the breakpoint. He's, like I said, he has a read. He's going to convert the first thing that he reads into an integer, use that integer as an index into that pointers, and then he's going to call that function that he's indexed into. And I believe I'll scroll up and I'll show you the pointers. That's just showing you the buffer. So that's the buffer coming in. So if you remember, there was like the very first part there had a 9. There's your 39 showing your 9. You can see it again right there. That's just printing at the buffer in, it's like I was trying to get the address. So there's the address, and at the bottom it's BFFF 330. And then this is the stack pointer. So you want to go from the stack pointer from that buffer to get to where your return address is going to be. It'll be like stack pointer, frame pointer, return address, if there's no parameters being passed from one function to the next. So there again, I'm showing you, there's your frame pointer. The ESP is your stack pointer. Once again, don't get too weird about this and worry, because the next thing I'm going to show you more in depth. I'm just kind of showing you the flow here. So once again, I'm in GDB with TUI syntax. There's the pointers array that I was talking about, 0, 1, and 2. 1 would be the get wisdom call, 2 would be the put wisdom call. But that number that we've calculated there is going to go way past that, and it's going to go to the stack. This is in the data portion of the code. So actually here is actually the math for what those address. That times 4 is because you're not a pointer to bytes, you're a pointer to addresses, so it's 4 bytes. So there's your 370. At 370 is the 350. That's the index. The next part, you see the 6E, 69, 2F. 2F is a slash in ASCII. So we're kind of like showing you all the pieces before we jump into that buffer. So here I'm going to show you the disassemble of that address. So what's at 350? And there it is. So this is the classic, do a system call to do exec. There's your pointer to your string, your pointer to the pointer to that string, setting up a 0 as your next parameters, doing an int 80 on i386 is the way you do your system call. What's in EAX is your system call number, which corresponds to exec. Don't worry about that. We're going to show more about that. But just kind of getting you acclimated to it. And so here is right before we're going to call what's in EAX. If you remember in that C code, it was the foo in parentheses. That's calling your function pointer. So there I'm showing you that your second parameter, or pardon me, your first parameter is EBX. When we dump it, you can see the 2 Fs, those, and that last 0 there I'm highlighting. That is your /bin/sh. That is your shell. That's why this is the shell program. The next address right after it, which is the ECX, that's your second argument. That's your pointer to your pointer, and that, you notice, was the address that we were looking at. See, 374 points back to 374. So now we're in our shell. I'm getting ready to do the int 80, which does the system call, once again, based upon what their parameters and their, there's the 11 for exec. I'm waiting. I'm just kind of printing them out here another way. And we're going to hit continue here in a second. By the way, if you watch, so this presentation is online. If you watch it on your personal computer, you don't have to make it full screen to be this big to show everybody. You may not have that bar going there. You should be able to read all this text. So there I'm just showing you how to print it out as a character pointer, and there you literally see the /bin sh. Here is the man page for system call, and it'll show you for the different architectures how you do that. And you'll see this multiple times in this presentation because we're going to do all three. But there is for i386 to do a system call, it's an int 80. The parameter is your number, and there's like another page down below that was showing you where your function call parameters go and which registers. It differs by architecture, but once again, I'm just showing you. I figure if I show you like 5 times, it'll stick. All right, so there's the int 80, and let's get this show on the road and hit continue here, please. Okay, so down below there at the very bottom, there's your actual parameters. And how do you know what those numbers are for like the what to put into your system call number for this i386? Well, you look in your Linux headers. We know we're on 386. We're 32-bit, so you look at that include file, and it'll be in decimal. So, and I just want to look for exec. There it is. It's 11, which is odd, which is the same number on ARM. I was a little surprised by that. It's 3B on x86 64. And I'm just going to go back down here to actually show you this next page. So once again, i386, arg1 to the system call is EBX, ECX, EDX, based upon how many. We're only going to use arg1 and arg2. arg3 will be null. And now you've seen the system call. Now look at the exec. See your path is at the beginning, the argv, and then the environment. In this case, we're just using a null environment, so it'll be null. I'm just going to jump down to the end. I'm going to scroll up. I'm going to show you the example usage, so it'll be a little clearer. I'm going to do a search, for example. Thought I did a search. I guess not. So there it is. There, that's our LS. That's our pointer to our pointer there. And then you just have that set as null. At the end of this, to terminate the variable argument, you have to put another null pointer. That's the same thing I just pointed out. So that's that. So all right, so some of the tools that I was using to do this with. So we're just going to wing it. So, so now that you've kind of seen the overview, let's show you what's happening with x86. We'll kind of have a funny slide for each of these sections. So like 20 years ago, 1996, Alf 1 or Elias Levy made the smashing stack running profit paper. There's a link to it here. This is just an aside, which we're running out of time. You got to watch this video. It shows actually that guy running. And so basically, this is his technique. So you have the stack before your string copy, which has a buffer, has an end. After it has a frame address. It has the return address. We'll see this over and over. What we're trying to do is put some no-ops in there, so that we have our shell code. And so I'm going to say that these are leading no-ops. This is our jump. This is his trick. Jump to this call, which comes here. That doesn't put anything on the stack, but then he does a call to start to go back up to the start of the shell code. When that happens, this address gets put on the stack. Since it's on the stack, he knows where it is. And then there's like the frame space or the buffer address here is, this is like the return address that you want to put into when you come back. That should come up here. And so alternate view, without so much detail, this is your buffer start. These are your so many no-ops, your shell code, and your buffer address. Basically, this is so that if you don't know where it is, this gives you many possibilities to find out where the buffer is. All right, so this is a demo where I'm going to take just a string copy, which is exactly what he was demoing with just a stir copy, and hopefully this will work. Very slow. So this is just that code explained and actually assembly. So there's your initial start to jump to the call. I have the Kraken label in there. There'll be some other labels just so you can see a little better in the object dump, but this guy at work, you find his code sometimes, release the Kraken. I thought I'd honor him. But so the start of your buffer, you're going to jump to the call, which is down here. And that doesn't put anything on the stack, but call the Kraken will. And right after the call is this label for the string, which then comes back up, puts that address on the stack, which you then pop. You're not going to pop it to do a return, you're popping it to get the address. And just move along. Once again, I'm trying to show here this is our goal. So we wanted to do that system call number, the pointer of the string, pointer string, your null pointer, and you wanted memory. You want a null there. And if you were to run this right before you get here, you want to make sure this looks like so. This is not that difficult, but that's like contents of and stuff. We'll bore you there. We're trying to move. So running that variant of the code with the hitting the wrong. So in this case, I'm running a shell to pass in args to pad no ops in front of it until I find out where it is, and then I can do my ls. So I'm taking that code, putting it at the top of the buffer, putting no ops in at the top of it, one at a time until I slide that down over to the return address. And this is just in bash code, it's no big deal. I'm not putting a postfix of the actual address to come back to, because I think I'm writing that in the actual string. This is the code. This is very similar to what Levy was showing. I'm not really worried about the vulnerable part. Actually, I am. The vulnerable part is the call that comes back up. So let's see. Now in this case, what this is different from the next one, and I will show you that one as well. This guy, the buffer is big enough that the shell code could fit inside it. If your buffer is too small, you're not going to be able to put all your code, so you're going to have to find where it comes into the entry point. So in this case, based upon the buffer size of the program that I was running, I was hitting in the middle of this code, so I just added the addresses for the return address in the middle, and then the jump jumps over it. So, and I had to put some no ops to make it align, but jump to resume here, which goes down, and then it continues over. There we go. So once again, it's just showing the same thing. The result is I get a shell. And since we're out of time, I'm going to skip this, but I just want to show you it's the same exact code. So I'll skip this one. All right, so for x86 64, the paper I was using for this was this guy, Unilcoder. I keep thinking it's Uncle Coder. I think UNL is like some kind of like language description for trying to understand computer speak or linguistics or something. But the joke here, it sounded kind of European, and I just kind of saw this guy with his post about Microsoft, and I thought it was like, hey, that's a good intro slide for him. So there were two papers. Once again, there was one in 2009, and then this guy, Unicoder. And I used his. I thought his was pretty clear and easy. Basically, just between 64-bit and 32-bit, you got more registers, you got larger registers, RSP versus ESP. It leads to a different ABI. The largest user space memory address is I think it's 27 bits, but just means if you put a 7, you're not going to get, it's not 27, you're not going to get all of those, and it will expand for you. So let's see. And I'm just kind of spacing these off because I know that I'll have an offset and of an offset and then the 3 Fs, and I didn't actually write that out, right? But let's watch this. So in all of these, I'm taking off some of the protection, which are there by default. Like I'm turning off ALSR, which is randomizing your addresses. I'm turning off the no stack protector, and I'm making my stack executable, because my goal is just to show you how it works, and then you can get fancy and make it more complex. I'm also making these buffers a little smaller so I can find them a little faster. My shellcode is, I think, 50 bytes. The buffer size is 64. So that means I need a minimum of 14 bytes to pad it before I can start putting the other stuff in there. This is the assembly, and there's a kind of a problem with NASM and Syntactic, but let me get this out of the way. All right, so now if you see this portion here, your system call number goes in RAX, and your args are in the RDI, RSI, RDX instead of like AX, BX, and CX. One thing I liked about what he was doing, and I'm kind of like using their models and dorking with them a little bit to get them in my style for what I want to do. In his example, he was just doing a cat of Etsy password. I really wanted a shell, but the thing I did like is right there at the top, doing the XOR of the 41. So at the bottom, the actual /bin.sh, there, I've got the shell. This /bin.sh had a 41 at the end, so it's nice and easy to get your 0 at the end of that string, because you can't put it in there. If you do there, it'll truncate the buffer. It's just XORing a 41 with it. And there I'm just saying run that program, BOF, which is a C program, passing in a string that's within the buffer, and you can see it goes to it. I do a lot of these, like GDB, changing parameters around, and then I'll make patch files so that I can kind of like peek and poke on things. And once I get it there, then I'll move it over to rewrite my assembly. So we're running the BOF program. We're passing it the shell code. We're going to run down there. We're at the string copy. When we're doing next, we're going like over instructions. We do a step. We're stepping into them. But if you're in assembly, you want to use the step I to do just much. So right there is the leave. So after we've done the call to the string copy, once we do the leave, the stack pointer is set up to point at your return frame. So you're going to have a frame address, and then you'll have your return address. So I'm going to print the RSP, which is your stack pointer. That's the top of it. And then there is what we're looking at for frame and return address. So, and I think I changed the layout next, because when you're in TUI and you do the disassemble, if you've got the assembly up, it doesn't always scroll. So I have to like, yeah, this will work now. Now it'll put it in the command window. So you can see, yeah, sure enough, there's our jump all the way down. It then calls back up here, and then you do your pop. You XOR. There's the 41 that I was XORing at offset 7 to get rid of my 41 at the end to give me a null. So now we're in the shell code, the DE30, I believe. Yep. So there's our calling down at the bottom. And now we're going to pop and come back. See what I'm getting ready to show. Or is it still going? So now we've popped, we have the address, and then right now, instead of doing an int 80, it's going to do a syscall. Instead of using a B, it's going to have a 3B in RAX, but the RDI, RSI, all of those guys have to be set up. And so I'm just showing you what the info for the registers are, and then I'll print out those contents just to make sure everything is in the proper place. I'm using the G syntax when I'm printing because we're getting 64-bit, and we're going to see instead of just 32-bit words. And there is the string. Once again, 2F is your slash, your trailing 0. And we're going to just hit continue. And so now you got a shell prompt. You can ls around your, and I'll have to exit that to come back into GDB. This seemed a lot cooler when I was doing it. This is like really boring. Okay. So, all right, we're good. Once again, like I said, the code is up there. There's a lot of notes in those GitHub links, and they're like my own notes. But you can kind of read like, what was he trying to do here? And I try to comment the GDB files as I'm doing them, just so I can keep track of where I'm trying to get things to work. And the source is there, and it'll make you can get all. You need a VM for x86 32-bit. You don't need a VM for 64-bit because your chances are you're running on that already. And then with QEMU, you can run an ARM, and that's something you can't do. I don't think so. I don't think you can do that with VirtualBox. Run an ARM on Linux without it. All right, so I think we're running out of time, and so I'm going to skip this. These are just some tools like how to take an object code and get a byte string, and it'll automate it for you. Those kind of things, just bash scripts. All right, so now this is where the fun begins. So don't stop yet, but there is. I'm trying to press this. So when I got to ARM on Tuesday, I was like, man, I'm running out of time to do this presentation, and I really don't know ARM at all. And I'm either going to end up in one of these two states. I'm either going to be like, I'm a god, or I don't know what the hell I'm doing. And I'm kind of leaning like I'm really on that right-hand column right now. But there was this other one, like, hey, writing code like this, you're picking up stuff and you're putting it together. It's kind of like a wizard, like, I'm going to summon a demon. Oh my God, I got a lemon or something else. And then I saw this post this morning when I was actually doing this, finished this presentation. That guy who right here, give him credit, he rocks the role. I need this book. All right, so when I kind of did the outline for this way back when, I was like, oh, what I'm going to do is I'm going to find the latest one and do that one. So it was the Zook guy. And then I was like, well, the return to P, that's too hard, and it's kind of invariant from what I've been doing so far. Supposedly what I'm doing so far isn't going to work, but maybe we can brute force it and get it to work. So I went back and I found some other papers, and I found this 2009 paper. And this guy, I've got to show it to you because these three guys, they rock the role for real. So once again, it's kind of in the style of the smashing the stack. But basically what he's going to say is, let's look at all of the ARM and thumb instructions, because ARM has two different modes. And let's look and see like how we can fix up alphanumeric white spacing. So remember what I was talking about in the other guys? I can't put a 0 in my buffer. If I put a 0 in my buffer, the buffer gets truncated. Well, you also can't put like a hex 20, which is a space, because then you would have two arguments and it wouldn't read the rest of that string. Can't have like an OD or OA, whatever carriage return line feed is. Well, these guys went in and said, let's look at all of the possible instructions, and then let's come up with this table of what possible instructions we can use. The column on the right is like why you can't do something, or if you can, how you have to limit your parameters for that instruction. Then he went into the thumb instructions, which are the 16-bit ones, and he came up with his list of possible instructions that he could use. So, you know, you can't do like a move R0, right? Because that has a 0 in it. And so I tried this, and I was like, this is just exactly what I'm saying. I don't know what this thing does, but I'm going to try it, and I can step through it and get it working. This is his shellcode in assembly, which is in thumb mode. This is the code to get the shell. 5 minutes, wrapping up, got to wrap it up. That much. I was like, that was incredible. Unfortunately, when I was doing it, it failed somewhere along that store multiple registers. So, anyway, I was like, hats off to those guys. So this other dude I found Wednesday, Salwan. I thought his was pretty clean, and I liked it. And I will just show it to you real quick. We got 5 minutes. We're trying to push. So basically, what he's going to do is he's going to start off in ARM mode, which is 32-bit. He's going to do this bit at the very beginning to switch to thumb mode by changing the address. So he's going to jump to the PC +1. That address is odd because you've added 1 to it, thumb mode. Then he goes down where he does the add R0 to 10. He's literally counting what from here at the PC, how many bytes are used to get to here. He's putting in a leading slash there to align it to the addresses. And then he's doing the same thing. He's going to do the exec with a system call. It's decimal 11. His R2 is 0. Up above, the pointer to the pointer, yada, yada, yada. And we're probably running out of time, so I won't do this completely, but it's very similar. So first thing I did was, I was like, can I get that? Oh, yeah, there was just one thing here, which I think this is why he's doing this. He has an SVC1. If you look back at the man page, and if I had time, I would show you, it's really an SVC0. So, but once again, you can't put a 0 in your buffer. So I think he was going to say, like, I'm going to write this out, and then I'm going to self-modify the code to put a 0 in that location. So basically, in the following demos, I do those kind of things with patching it. So as it's running, I patch it with GDB. So I can get this guy to get a shell, or to execute a shell statement, so do an exec. When I tried to put that code into other code, didn't work. And I think part of the problem is you're in thumb mode, and these later ARM GCC results, you're already in thumb mode, and then trying to switch over. And I played games with don't do the switch, I'm in thumb. You can see in the videos. Changing the addresses from odd to even, what I was doing the call. But that's that. Take one is like take one of a million, but it was a good stopping point, take two. And then these are just the credits and references. And then the takeaway for the last thing I'm going to say. What do you take away from this? So I used a lot of simplified methods. I was disabling things. So to prevent like the easy hacker exploit guy coming into your code, and that's the whole point. Learn how to do it so you can prevent it. What are you going to do? Well, you know, of course, you're not going to disable the ASLR, so they'll not have the same address each time they run it to try and find it. You put in exec shield to prevent stack execution. Employ like a find exec stack, defining the executables lying on your file system that are executable. One of those videos, I'll show you how to use readelf-l to do that. I also, the very first one, I was doing a GDB attach, so I'm like running the program and then attaching GDB to it. You can disable that. Some of the stuff after this, I'll show you how to strip your executables for stab strings and symbols for the actual, what you're calling, like you won't see main. Validate the length of all your buffers on all input sources. So anything that's coming in being, you need to validate, is it good? One of the things, and employee like your string, stir in copies, stir sprintf, all that stuff. Stat canaries, make sure your length is greater than what your length of your buffer is. Use that filter, make sure if you're like taking text, they only send text. If they're only supposed to be sending, digits 0 through 9, white space that. Avoid running as root, because once you get the shell to that program that's running, it runs with that process ID. So if you're running, like one of these guys as root, well, that's the only reason I'm putting an onion here is it's like layered defenses. You're just putting a whole bunch of blocks to get them to stop. And time is up. Thank you, folks. I enjoyed it.